Okay, so what have we got? We have got dx tilde mu d uh, dx alpha is equal to, and we will have delta mu alpha, and then we will have plus d alpha zeta mu. In exactly the same way, we've got dx tilde mu dx beta is equal to delta mu beta plus d beta. Uh, oh, come on. Uh, Plus d beta zeta nu. Okay. And now what we can do is we can take these expressions in the green box and plug them into the black box. So let's do that. Okay. So what do we have? We've got eta mu nu. So we've got eta mu nu. Okay. We've got eta mu nu. Then we need to multiply by dx tilde dx alpha, which we've got here. So we'll have delta mu alpha plus d alpha zeta mu. And we need to multiply by dx tilde nu dx beta. So we will have a delta. We will have a delta mu beta plus d beta zeta nu. Okay, and this should be equal to eta mu nu. So now let's see what we get. So we need to multiply these two brackets. So I could multiply this first term by this first term. Well, these will both multiply onto eta mu nu. The delta mu alpha will give us an eta alpha, and the delta nu beta will turn the nu into a beta. Then we could multiply this d alpha zeta mu onto the d nu delta nu beta. So the eta mu nu will bring the mu index on zeta down, and the delta will change it from a nu into a beta. So we will get a zeta beta. So the zeta beta I got by multiplying the zeta mu into the Minkowski metric. That brought the index down and turned it into a nu, and then the delta function turned it into a beta. And then we've got our d alpha. This term comes with a plus. And then we've got this term, and we multiply this delta over there into that term there. So what does that give? Well, again, the eta mu nu onto the zeta makes it a zeta mu downstairs. And if we then multiply by the delta mu alpha, the index on the zeta will become alpha. And the derivative stays d beta. And then finally, we've got one last term, which is when we multiply the zeta onto the zeta. And now we cash in on the fact that our zeta is infinitesimal, so we don't need to keep that term. We can drop it. And this should be equal to, oh, sorry. So in this equation, this should have been equal to eta alpha beta. So let me just change those indices. That was a typo. So let me write the correct indices. This is eta alpha beta. And then what you see is, so this is eta alpha beta. So this term cancels against that term, so that the equation that we'll end up getting says d alpha zeta beta plus d beta zeta alpha is equal to 0. So let's just remind ourselves, what does this equation describe? This is the set of coordinate transformations that we can perform. That's what we were doing over here, performing coordinate transformations. And these coordinate transformations will preserve the form of the Minkowski metric. So we usually say that these are isometries. So iso meaning the same, metries for the metric. So these are symmetries of the metric. And this usually gets a name. It's called the Killing vector equation. So this is the Killing vector equation. Now, you might think that with the name, the Killing vector equation, you might think that there's an interesting explanation of why it's called Killing. Well, not such an interesting explanation. Killing was just the family name of the first mathematician who discovered this. And this is just describing the coordinate transformations that preserves the Minkowski spacetime. And zeta alpha or zeta beta, this would be called a Killing vector. What we're going to do is we're going to solve this equation and we're going to see what Killing vectors we get. And from the Killing vectors we get, we're going to be able to identify the Poincare group. So 4 translations and 6 Lorentz transformations. So we're giving a way to derive the Poincare group, and we'll be able to generalize this slightly and derive the conformal group in this way with a few slight generalizations. Okay. Now we've done all of this for flat Minkowski spacetime. So this is the Killing vector equation for flat Minkowski spacetime, but there is a curved space generalization. So in general, so curved space generalization, hey, come on. Generalization. And what is this curved space generalization? Well, this would be the set of transformations that would preserve some general metric of a curved spacetime. You are going to derive the curved space generalization of the Killing vector equation. So you'll just repeat my exercise with the only difference being that now you will replace eta mu nu by g mu nu, some general metric, and g can depend on x. So when you do the conformal transformation, when you do the coordinate transformation, g mu nu of x itself will also change. You need to take that into account. What you will find if you do it correctly is the following equation: d beta zeta alpha plus d alpha zeta beta is equal to 0. So this is the Killing vector equation in curved space. That's the equation that you'll obtain if you do things correctly. And as usual here, we're making reference to the covariant derivative. And the covariant derivative d mu zeta nu is written as, well, we've got the normal derivative, but then there's a correction to this, and the correction to this uses the Christoffel symbol. Okay, so that's how you would write it in GR. So that you're going to derive on your own, and that's the curved space generalization. So this would be the Killing vector equation in curved space-time for metric g mu nu. Okay, good. So what are we going to do next? Now we're going to look for solutions to the Killing vector equation and really show that we can recover the Poincare group. And then we'll move on to talk about what's the correct requirement for the conformal group. And we'll get a differential equation that we'll solve to figure out what the conformal group is.